don't think they're even. Are you college graduate? Anyway, if he had had a good education, Rod Neal and Stan Gleason would never start this experiments in the laboratory in the back of a welding shop. Well, they're crazy, but they're not stupid. They're pretty bright young men, and they've got a high learning curve, and it's been a privilege to kind of help suggest some things to them over the past couple of years, and Rod has given me the privilege of presenting this, not a scientific paper, but a prelude of information which will have to become in a scientific paper in the very near future. So Rod, we want to congratulate you on being crazy, along with some of the rest of us. Just a quick announcement. The paper that we're presenting here is on the back table. It's the one with the yellow card on. It's a freebie. Please pick one up. So for a real short time, won't cover it all. There's also a free copy of New Energy News. Please read the front page editorial. It's based on some comments that Dr. Bacchus and Dr. Lynn have suggested about getting organized. Your papers will be published immediately after this conference in issue 3 of volume 1 of the Journal of New Energy. Volumes 1 and 2, issues 1 and 2 are available. Issue 1 was the proceedings of the last conference. My wife and I mortgaged the house to get this started, so it's not a freebie. You have to pay for it. I brought 10 copies, but we do have a special price of $30 for this conference. Now to get on with the talk. Basically, we're talking about a relatively simple electrochemical cell. We cannot tell you the details at it right now. The inventors have been very strongly advised not to give out all the information until they tidy up their intellectual property arrangements by filing patent applications appropriately. Basically, their various high mass elements can be split into lower mass elements. The operation of the cell it has a lot of different parameters. Of what you get from the cell depends on the various changes that you make in the temperature, the molarity, whether you use AC or DC, whether it's pulsed, what the frequency is. The electrode configuration is very important. It turns out there's only one electrode configuration that really works well. Other choices of electrodes do not work as well. It's a very unusual, very strange discovery, and in my opinion, in my technical judgment, a very important discovery. In the processing of their experiments, they generally will take make up a solution of a metal salt, put it dissolve it in the water. Maybe they'll make 500 milliliters. They'll put half of it, like 250 milliliters so they got to be before and after solution. After they get through their processing, the joule energy is normally enough to boil a lot of the electrolyte out. They have learned to capture gases. They measured the gases to see what's involved there. At one stage, it was suggested that they go to using a radioactive material, so they chose to use thorium nitrate. You can measure with a Geiger counter. After you get through, you can measure the contents of the beaker or the reactor. You can look at the electrodes. You can measure those. You can measure the off gases and determine if there's any radioactivity in any of those sources. If they're not, then you assume that whatever radioactivity there was is still in the sample or perhaps has been modified. Typically, a reaction would go something like this, that you put in that's nice. Try one with try transparency. This is the thorium, this is the decay of thorium that occurs naturally, and it goes through these steps with radium activity. What is that one? Actinium. Thorium and radium again, radon, polonium, lead, bismuth, polonium, tellurium, and back to a stable lead. So in that series of isotopes that have come from the thorium, here you have the variety of half-lives from 1.4 times 10 to the 10th years for the natural thorium. By the way, only thorium-232 is found in natural thorium, just the one isotope. So here are 5 years, 6 hours, 1 year, 3 days, 55 seconds, 0.1 second, 10 hours, 60 minutes, 298 nanoseconds, 3 minutes, and then down to stable lead. So these half-lives, so you get a distribution of these isotopes. And the interesting part is that all of the isotopes, except for the one as they decay, except for the one that's only lasts for half-life of 298 nanoseconds, all of these give out gammas and of specific energy levels. So basically by using a gamma ray spectroscopy on the samples, before and after samples, you get an idea of the amount of radioactivity. So what they have found as a typical an experiment, by taking the total counts of the same amount of material before and after, measuring the amount of radioactivity, found out they reduced the radioactivity in a batch process in like a 1 to 4 hour treatment, reduce radioactivity by 40, 50, 60. The best they've done is reduce it by 77%. Because of that, we think there is a great opportunity for this type of work as after. By the way, we don't believe any of this until we have an independent third-party verification. Funding has been arranged and a third-party verification is imminent. One of the ideas that, of course, is to take this type of a reactor after it's greatly developed and improved, and this would be, for example, what a reactor might look like with the anodes and or with the electrodes and so on. Calling that the reactor cell, then, the idea is to take the radioactive material, the slurries, and run it through the reactor cell, take out the stable elements through the chemical separation, and recycle the material that's still radioactive. In talking to some of the people with the Department of Energy, they suggest, well, an advisor to the Department of Energy, by the way, suggests it may be necessary to have a chemical separation and before the reactor. This is probably particularly true for taking out the cesium and the strontium that are so, the problem is so bad in getting into the food chain and into the bones of people who eat the food. In Belarus, 10% of the children are healthy, 90% are somewhat to severely damaged by radiation effects from the Chernobyl accident. Chernobyl, as you probably know, is about 10 miles south of the southern border of Belarus, and the wind was blowing over Belarus at the time of the Chernobyl blow-up. In the United States, the Department of Energy has something like 156 sites. Here's one that's been beautifully positioned in the bend of the Columbia River, so the nuclear reactors that they've set up here could use the cooling water. In this area, particularly in these areas, there are 66 million gallons of radioactive slurries in some 177 tanks, and 67 of those tanks are believed to be leaking. And well, not before too long, will be in the Columbia River if it isn't already. Horrible problem to clean up. Here are the various sites in the United States that show the just very quickly, the dots here are the locations of the sites. Here is the various amounts of radioactive material that needs to be cleaned up. This is a typical, whoops, that's typical Hanford. There's a typical tank. They're buried underground. They eventually put in double hull tanks. So the single hull tanks, about half of them they started out with are leaking radioactive material. So the basic thing that is very important, if this technology that you gentlemen are all involved in, if we can really make the changes in transmuting elements, particularly in transmuting these radioactive elements, we have a gift to the world that is beyond measure for its value in terms of human health. So the conclusions that I would like to point out, I think the discovery of the Neil Gleason effect is an extremely important. It's an electronuclear transmutation, but it must be replicated by independent third parties because of they've had very strong inputs from their advisors that they do not give out at this time exactly the materials and the configurations that should be used without signing appropriate strong non-disclosure agreements. And any of you've seen Rod Neal, talk to him about that. We think that when replicated, this is going to be one of the more collectively, all of this has led up to all the work many of you have been doing, leading up to the possibility here of cleaning up this radioactive waste. And by the way, the estimated costs for cleaning up the waste byproducts of just the Department of Energy's weapons work that's been done over the past 50 years is 265 billion, that's with a B, billion dollars. About $50 billion, for example, has been estimated to clean up the Hanford site. We think we're now, because of the work all of you are doing, we're standing now at the verge of being able to do something that's very important for mankind. And because this is Friday the 13th, that's my final comment.
Any closing comment?
Al, how many times have you been able to do this? Or
these gentlemen got a before and after, a sheet of documentation where they've taken their before and after samples and had commercial laboratories give them the test results. I imagine about 40 or 50 samples, Rod, is that about right?
Several hundred.
Your data? Yes?
Several hundred.
Hundreds.
Several hundred.
Okay, over 100, all right.
But I look at your table of for the decay.
Decay. Decay, have radio decay.
Okay, I have some data here. I can show you the before and after counts on a typical. I've got the data here. I can show that to you. I don't have a slide for it, but it goes down by about. The interesting part about it is all of these isotopes reduce about the same. However, there are significant changes which indicate there are probably some unknown nuclear reactions going on, but not only is the thorium being lost, but also all the daughter products of the thorium decay.
Are you identifying all the gamma rays coming out of this?
The gamma rays is the same as the identify with the table for the gamma rays.
Well, yes, if you, I'll show you the data, Dr. Kim. You can see all the different, both the before and after tests and all of it in 50 different channels.
Hal, has the process been shown to be technically effective and potentially cost effective for the entire zoo of isotopes that contaminate a site like Hanford?
It's energy intensive, but my estimates is that it would, at the present time, the estimates are they'll cost about $2,000 per kilogram of material, radioactive material per year, packaged, transported, and stored for 10,000 years in Nevada. My very rough calculations would indicate something of the order of a couple of $100 per kilogram of material transmuted.
Yeah, that's the cost part, but technically, will it handle all of the contaminant radionuclides?
We don't know.
Okay.
The best evidence that we have is from this data from the radioactive isotopes of the decay of thorium. Now, we're getting some data with radioactive they don't have a hot lab, they don't have a nuclear regulatory license to work with a hot lab. That's got to be planned, it is planned and will need to be done. But it does appear from the various materials they've been able to transmute, change down heavy elements into smaller elements, it does appear that it'll be effective across the board. Now that's an excellent question and a cautious answer, let's put it that way. We need to find out. It's very important.
Okay, thank you, Bob.
So welcome back for the afternoon session. Dr. Lynn, our host, is first speaker this afternoon, so pleased to welcome you.
Thank you. The topic of my talk is anomalous radioactivity and effect element as a result of heating in organic mixture. This work is done by me and Professor Barclays. This work is done in 1992. Recently we got a release from the owner, so we can have a talk. Introduction. Now, the transmutation experiment is induced in 1913 by Thomson. He reports that Ramsey and Patterson in 1913 discovered helium and neon by the vacuum tube discharge. So basically, he used positive beam. I guess in that time, people have not understand the electron. So I think the electron beam, but the paper used the positron beam. So that's the first talk we found in the document. Now, second I want to mention is the carbon to iron experiment, which is induced by Kushi and Osawa actually more than earlier than 1965. So basically, two carbon rock have arc discharge, then find some kind of iron. And later, three group almost done in same time. When Japanese group Nakamura, Sandra and Box in 1994, and Dr. Singh India in 1994, they published in almost same time, discover iron to carbon to iron reaction. However, the isotope abundance is found not so big a difference. So that's the experiment result. Now the third one is called gunpowder method. Gunpowder method is used for very long time, maybe beginning this century, which basically in the minor company use gunpowder to increase the yield of gold. So now still have a question, one is maybe is further extraction or is transmutation. Now, beginning discuss our experiment result. The experiment result, I separated two parts. One is called anomalous radioactivity. Basically, we record the beta radiation decay. Second is unexpected element. Basically, we detection of gold and other elements by the origin material. Some is without gold at all. First is anomalous radioactivity. The experiment then is April 14, 1992. The chemical mixture, composition of the mixture is 7 compound, basically carbon, potassium nitrate, and sulfur, which is black powder main form. We added some other chemical. And all the chemical is bought from the chemical company. The purity is not so good purity, but there's no precious metal inside, or at least the precious metal is way less than 1 ppm level. So that's the chemical mix. The express seeding is just fire those chemical mix because it has carbon, nitrogen, and sulfur, so very easy to burn, just like gunpowder. Now after mixture fire, then we record the beta decay. The experiment result, one typical experiment is beta decay functional time. We record from 45 hours totally, so which is more about 2 days. And we record beta count from the beta counter. And that's the first experiment, that's midnight. And then secondly, do experiment, and thirdly, record again. The curve looks like exponential decay and with pretty good shape. The half-life time of this beta decay curve is about 17.7 hours for the beta decay curve. Now, so now what's the experiment explanation of this experiment? First, of course, is someone suggested the vapor adsorption, because this after fire, the product is very easy to absorb the water on the vapor. So the potassium have potassium will have some kind of radiation which will be recorded by beta detector. And if water layer becomes thicker, then you record the beta will become small and small, which is suggested by Nomansky. The second is nuclear transmutation, which is from platinum 197 to gold 197, which half-life time is 18.3 hours. Now, we discuss unexpected element. Total experiment we did is 17 experiments from April 1995 to January 1993. The proceeding is very similar with I talked a couple minutes ago. And the sample after fire, the sample we send to different places. One is called Bonder Player in Ottawa. They use fire assay and ICP method. And we send it to Cicero Laboratory in Australia, is ICP and atomic absorption. We also send Chemivax in Nevada. They use fire assay ICP technique. And Mintech in South Africa, they use 4 different methods plus ICP and mass. So we send the cell sample for different companies in different countries by different methods. Also, we did it by ourselves, which is use fire assay and ICP and neutron activation and use other techniques by ourselves. Now, the first experiment is we call, just give arbitrary name, called Thermo 1, which is in April 30, 1992. The chemical composition mixture is all those things. And basically all is by chemical from the chemical company. The purity is basically more than 99%. The analyzed result of the Thermo 1 is the gold analyzed, this company say no, Cisco say no, Cameo we use fire assay method, basically no, but only one run. One run means after burn we have a lot of product. Then we separate different products to use 5S method. Most 5S get no result, but one run we can see visible gold, I mean very big piece of gold of EDS, which corresponds to 148 ppm by ICP method. And now, from now on, when I talk to ppm, I always respect to the original mixture, which means the original total weight of this mixture. For example, this mixture is like 1,500 grams. So when I talk to ppm, it's relative to this 1,500 grams. So now also, if we send signal to neutron activation, we saw some small signal of gold too. Now platinum, bound Craig and Cisco and TMU both get twice the increase of platinum signal. Twice in here we already counted the concentration factor, because before reaction is, for example, is 1 kilogram, after reaction only 500 grams. So when I say twice, which means after reaction product really is 4 times larger than the product, then we can say, consider concentration factor of double, so become twice. And also irradiating is signal detected by neutron activation. That's the first experiment. Now, second experiment is made on May 22nd, 1992. The chemical position is this way. Now, notice what's different. Which one is the nickel? Is originally have nickel. Now we drop nickel. We change it to CaO. Second, we drop the palladium. Originally have palladium, if you notice it. Now we don't have palladium. So tiny change of the chemical mixture. The result is like gold from Chemivax before the reaction, which is 0.3 ppm, which is reasonable in the chemical, when we buy chemical. So basically 0.33 ppm is in the elevated range, so very low, in almost a low limit. Now to greater than detection limit. So the detection limit, I asked them how many millimeter they transfer to our is 100 ppm. So it's way up the detection limit. So we don't know how much, but it's more than detection limit. Bound crater get originally to 0.12 ppm to 450 ppm. The MinTech is from 4 ppm to 420 ppm. And the TMU is from the have 3 experiments. The first is 0.4, then second is 253 and 240. So basically, you can see is about 200 to 400 ppm from the thermal 2 experiment. Now plating, remember this experiment we don't have any plating, so it's also from the 0.4, 0.5, 0.3 to like 1 or 2 ppm from 3 different companies by 3 different methods. Now the third experiment called Conserver 3 is May 27, 1992. This experiment uses basically is gunpowder, mercury, lead, and like minimal 1. Minimal 1 basically is some kind of sand, is SiO2, but it's natural sand. Now, this experiment we do 2 times. One is like this kind of experiment. Second is comparison experiment sample, which means without mercury. So the 5-SF, we use 5-SF, produce 3 milligram of precious metal, which is correspond to 50 ppm, and compared to 0.8 bead, from the comparison sample. Comparison sample is without this part. Now, there's no more analyze for this sample, for this experiment. Now, thermal 4 is exactly with thermal 3. We use the minimal 2. Minimal 2 is the sand containing 1.6 ppm of gold and 2.8 ppm of silver. So in the 100 gram, there's 1.6 and 4.8. That's different with minimal 1 and minimal 2. The result of thermal 4 is a quite large amount of visible gold, about 47.3 milligrams of the after 5 acid and comparing it, we got one piece of precious metal which is gold color, is like gold, which is we analyzed by ICP. So after that visible gold, we then dissolve in the acid, then send to ICP. We analyze which is equivalent to 1700 ppm of gold. That's okay. Now this gold is with respect to the minimal sand, not with respect to the total chemical compound. With respect to only the sand. So that's thermal 4. Next experiment, we want to duplicate it, so we made a thermal 5. Thermal 5 as the composition is the same as thermal 2. Thermal 2 is not sand, it's a pure chemical. Without nickel, witut plating, we add CaO, the thermal 5. The thermal 5 is exactly the same as thermal 2, just duplicated. Use 5 as ICP method, we got 178 ppm of gold. That's with respect to the raw material, including all the silicon oxide, whatever, carbon, everything included, is 78 ppm. Now, that's the basic experiment we did in the first 5 runs. Look like it's pretty nice. Unfortunately, later, we really didn't get good results. For some, I don't know what's the reason, but anyway, we got get good results. Now, later we know thermal 6 to thermal 17, which from June 1992 to January 1993, which is we detected gold by 5S plus ICP, and only in the thermal 10 we got like 0.3 ppm. It's very few, and the other run we didn't get anything. And the beta decay, we run thermal 13, find half-life time is 23 hours. Now discussion. So 1 to 2 mathematical order of magnitude enhancement of gold is observed in 4 experiments. And now those experiments is confirmed by multi-independent analysis using several different methods and executed by various organizations from different countries, different companies, different methods. Now, if still someone say maybe it's a better extraction, but in most runs, except thermal 4, is use chemical. So pure chemical in the experiment. So we should exclude the extraction method. If extraction must be original in the sand, in the minimal sand. Therefore, we cannot reproduce this result in the later times. So that's the basically discussion of the work. Now, also we observe the radioactive decay, as mentioned, which time is very close to platinum-197 to gold-197. Of course, there's still one possibility of vapor absorption. So which means this work we still maybe need to do more work for this kind work. Unfortunately, we don't have field support. Actually, we still have money left, but the project is the money is frozen, so the project we cannot continue. So finally, I want to say this work is supported by Bill Thielander, the Philadelphia project. So thank you for your attention.
Time for questions.
Monty, yeah.
Yeah, I would like to remember the same thing that I told last year about this test. That we were so blindly concentrated upon gold that we could not see that that kind of mixture makes always nuclear reaction. Only not always makes gold. When I tested something like more than 100 tests with little change in the formula, looking for 60 elements, I could see changes from 10 to 12 nuclear reaction every time. Sometimes at gold, sometimes not. But nuclear reaction always happens with this formula. You have to check for a spectrum of at least 60 elements. Then you shall see that damage. So,
Yes, quite right. We only look for gold in later experiments. We should have looked for the other things.
I looked and I found.
Yeah, you're right.
Any comment?
When you said you couldn't reproduce them, how many times did you try?
From server 6 to server 17, which is 11 or 12 times.
But I must explain something. After we had this grand success as we saw it at this time, we stopped doing these experiments for about 6 months. We were chasing the gamma decay. We talked to Professor Naslitz about the beta decay. He pointed out to us that there should be the corresponding gamma decay. We had a lot of trouble with the instrumentation. Went on and on and on looking for gamma decay. Never found it. And then after 6 months, maybe 4 months, we went back to these experiments. But by now the team had shifted, you see, and they weren't the same people working. And furthermore, one was trying to leave and get another job, etc. So the psychological aspect of the team had all changed by the time we got back to doing these experiments 4 or 5 months later. And that may have had some influence.
Just a technical question. Does this really blow up, or does it just burn?
But
It burns.
yeah, because it's black powder, it's not explosive.
It won't explode.
Yeah.
Okay.
I shall show later what is how it happens. And that
Oh, okay.
an old photograph of such kind of
Yeah.
reaction.
Let's see it.
What is the temperature?
Temperature. I'm not sure, we didn't measure it. I judge from color, maybe from
Well,
800 to 1000
Yeah.
C. Yeah.
I used to do a lot of optical pyrometry. Just judging it, it's in that range, 800 to 1,000.
That's from color.
When it's burning, how long does it burn last?
Depend, basically the 1 minute to 2 minutes. Depend on weather, maybe in July, maybe a little shorter, wet, a little longer, but mostly it's from 1 minute to 2 minutes.
Other questions?
Not,
Thank you for getting the 12 big rocks, synthesis of iron via arc discharge through activated carbon. We have a light.
switch.
Well, I wanted to, first of all, thank Dr. Bachris for the effort, Dr. Lim, Dr. Marley for the effort they've done putting this conference together. I've been involved in organizing a few conferences, so I know how much work it really does take. It takes hours and hours of time, a lot of volunteers. And after last year's conference, I was kind of snooping around the Texas A&M Department of Chemistry, and I discovered what it is that causes the friction between Dr. Bachris and the rest of them. There they are, and the notation says, I've discovered a way to turn this lead into gold. Drop it on your foot and collect disability insurance. And I believe that low energy nuclear reactions is going to be the brick that finally drops on their head. So, one of the things that interested me was the old experiment that I'd seen bandied around for the last 10 or 15 years, the Osawa experiment, that reputedly was a transmutation of carbon and oxygen into iron. And I wanted to repeat that because it was a rather bulk experiment. We weren't dealing with micrograms. We were dealing with very readily observable quantities of material. I thought it would be a perfect demonstration for those that were rather doubtful in the area of the possibility of low-energy nuclear reactions. And so I went back and attempted to duplicate as best I could from the scattered literature that I had access to what the actual parameters were and what the actual experiment was that was done by Osawa, etc., back in the early 60s. And for those of you that aren't familiar with that experiment, it was based on Eastern principles of yin and yang, which if any of you know anything about martial arts or acupuncture or some of the healing aspects of Oriental medicine, you will understand that that's a very powerful concept in Eastern culture, the possibility that there are positive and negative forces in effect that can cause other effects that are not normally observable. And that's based on yin and yang. Here's an example of a periodic chart that Michio Kushi put together. And in it, he states that this particular chart of the elements reveals that lighter elements are gradually transmuting towards heavier elements, and heavier elements are in turn transmuting back into lighter elements, though it may take some thousands to millions of years in its natural process. Especially the transmuting speed of peripheral elements is much slower than that of central elements. That would be the helium, hydrogen elements are the elements that are more readily observed as being transmutable, and it's possible that what's being seen in cold fusion and other work are these very easy to transmute elements occurring in the reaction process. So basically the original Osawa-Kushi experiment consisted of taking a power supply, which I've seen described as both AC and DC, depending on what literature you look at, and connecting that power supply to a carbon rod and stirring carbon powder, and then removing from that carbon powder magnetic materials which were reputed to be iron. So we started out with a similar setup in which we used a 50 amp source from a house circuit breaker, a home circuit breaker. And we limited that current by using a 15 millihenry choke. We used a carbon rod, or as I'll tell you in a minute, an aluminum rod to stir the activated carbon for periods of up to 40 minutes. So basically you sit there in a very uncalibrated stir mode. You stir the carbon with the rod and you see a lot of sparks and basically a short circuit occurring. There's an arc discharge occurring between the carbon rod and the activated carbon or carbon source that you're using. We also used because we'd seen described this particular experiment with a copper plate and a carbon rod, we also tried an aluminum rod and aluminum plate of 6061T6 material in order to eliminate the possibility that there was some type of interaction between a carbon rod and a copper plate. And we did find the same results whether we used an aluminum rod and aluminum plate or a carbon rod and a copper plate. So that led us to the conclusion there really is no dependence on the materials that you're using for a base plate and what you're using to stir the material with, and we're assuming that the effect that occurs is basically due to the carbon arc, the spark discharge. Now once you stir this material, I have a demonstration here which perhaps you can see. This particular material that we used was 60 mesh activated carbon. We also use charcoal from Mallinckrodt Supply Company. And rubbing a magnet over the material beforehand, you will not pull out any magnetic material. But this should be very easy to see that once you stir that carbon rod on the material, you pick up with the magnet a considerable amount of magnetic material. And that is pulled out fairly easily after about 10 minutes. We also used in this experiment coal. Since I had ready access to coal of the type that's used in power plants, coal consists of between 40 to 80% carbon, depending on whether it's anthracite or sub-bituminous coal, which is what we have in northwest Colorado, which is about 40 to 6% carbon. We tried doing this with a carbon source, and we used a carbon dioxide supply of gas to bathe the coal in during the arcing process, basically to keep the coal from burning up. Because once you start that arcing process, the coal will start burning. So we suppress the fire in the hole by using the carbon dioxide gas flow. Now this is an interesting graph I found when I looked at Dr. Bachrach's and Sundaresan's paper on the amount of material that they removed. This is a plot of magnetic material removed versus time in minutes from 0 to 40 minutes, and grams of material from 0 to 0.35 grams. The lower chart shows how much material is pulled out after each 10 minutes of processing. Process for 10 minutes, let it cool for 5 minutes, process for 10 minutes, let it cool for 5 minutes. And each time you pull out a certain amount of material. It turns out that there seems to be a diminishing point of no return in this curve, which shows the sum total of the material pulled out. This curve tends to be going up and leveling out to a point where you're not going to get any more material out of the pile of carbon, no matter how much you stir it and spark it. And that shows up again here in this graph. The grams removed versus time tends to come up and level off. Now this is one of those papers that's kind of in process. I just called the analysis house that was doing the chemistry on the results, which was we used Standard Laboratories in Casper, Wyoming, and the Colorado Assay Company in Denver, Colorado, who have a very reasonable price. I think it was $7.50 for each analysis of how much iron was in the carbon. These guys have been in the processing business since the mines first started in Colorado, and they're quite reasonable if any of you are looking for a source of analysis. Now here's the kicker. And somewhat confusing based on what Dr. Bachrach has found and what Ishii has reported. When we first tried this experiment, we went to the chemical supply house and asked for carbon. They gave us this Mallinckrodt charcoal, which was 100% carbonized material, and supposedly no heavy metals, no iron, although the percentages weren't available. They didn't have ppms available to us. But when we first used the very fine powder, the charcoal powder, we found that we could not get any iron formation in the arc, which is why we went to activated charcoal, which we could get from a pet supply store.
Can you show the composition of your carbon?
The Mallinckrodt didn't have it.
Can you show the composition, the analytical composition of your carbon?
No, Mallinckrodt had not supplied us with that, and we need to get that analysis done. They just say that there was no...
A good analysis of the before should be important.
Right.
Next time that you try with a graphite raw hyperpure.
The point I'm going to get to address that is, The activated carbon we did have analyzed, and we found it had 3.8% iron in the carbon. Okay. When we pulled out this material here and had it analyzed, there was only 1.48% iron in this material. Doing the math on what we had here, we found that there was an order of magnitude less iron in this particular sample that we pulled out than existed in the total sample that we were processing, leading us to the conclusion that the iron in the sample was pulled out because we're using a charcoal or a carbon purification process which magnetizes the material in the carbon and then allows us to remove it with the magnet. So we were not pulling out more iron out of the sample than existed there originally, even after 40 minutes of processing with the arc. Which seems to be a contradiction of the shallow experiment. The activated carbon, this was another experiment we ran, and the activated carbon before the process, the iron content was 3.8%. The lab doesn't have the ability to measure nickel less than 0.01%. And the silicon is 4.01%. Now, after the process of storing the arc, the material that's left in after the magnetic material is removed, in other words, the slurry that's left after the process that's still in the bin, we found 3.3% iron was left. Well, that's reasonable because we're pulling out iron with the magnet. The silicon dropped substantially. In the sample, the magnetics material that we pulled out of the process, the iron content was only 2.48%. In other words, this material I just showed you was only 2.48% iron in the magnetic material we pulled out. The nickel, not measured. The silicon, however, content of the material pulled out was 4.67%, so the silicon ratio went up. Now, based on what we observed, I looked at a paper that Dr. Bacchus had done, in which they did a number of experiments versus time and pulled out a number of micrograms. This is the experiment where the carbon rods are in water and there's arcing between the carbon rods and the water. The material falls to the bottom. They analyze the material on the bottom and look at the micrograms of iron in the material at the bottom. And they had 3 sets of electrodes. They used electrode 1, electrode 2, electrode 3. And they got kind of a scattered data plot here and drew a line through it this way. And I looked at that and I said, well, maybe this point right up here is a bad data point. And if they use electrode number 1, which is the round circle, and they follow this curve, this is what they pulled out in 1, 3, and 5 hour intervals. Here, they're going basically down to a point where they wouldn't get any iron. The same with electrode number 2. At 1, 3, and 5 hours, they're getting to a point where they wouldn't get any more iron out of the sample. Possibly their electrode 3, if you ignore this, if this is a bad data point, you could say that this particular experiment would also tend to fall along the first 2 sets of electrodes. And it would reach a point at which you get no more iron out of the solution. That's just a possibility. It would be expressed perhaps a little bit better on this chart. So that with time on the bottom and number of micrograms being pulled out on the top, you see eventually for those first 2 electrodes, this set of electrodes and this set of electrodes, you're going to reach a point where you're not going to get any more iron out. And the number 3rd set of electrodes that was plotted might fall somewhere in here rather than up here. Anyway, that's just a particular suggestion that I had when I looked at that data based on the experimental work that we've done, that there is possibly a point of no return. Now, in talking and also looking at the Bacchus data and talking with Chris Akbar at the Cushing Institute, since actually 2 days ago, it's become evident that current density plays an important part in the formation of the amount of iron in the sample. The Bacchus and the Sundaresan paper both showed that with higher currents you get less iron in the sample. And the Cushing Institute people that are working on this problem are using about half to a third of the voltage and half to a third the current that I was using. And they say that they are getting excess iron, more iron than is originally in their sample. So that's another avenue that I need to investigate, and that they are investigating, is that the lowering of the current density is a key factor in producing an overabundance of iron, and an abundance that goes beyond the amount in the initial sample. So basically, I wanted to end this on the thought that, from what I've seen, it may be that the Osawa experiment is an error, although it's very fortuitous that based on his theory, he sparked research at the Atomic Research Institute in India and also here at Texas A&M into another process that may have produced iron in excess of what was occurring naturally. That's about the result of our work now, and we want to go back and look at current density and see if we can get excess. The reason that we like this experiment is because if it is true that you have excess here, it's such a gross and bulk demonstration to the doubting Thomases that it would be hard for them to refute it. So we're kind of hoping that it works out, but as I said, as of this time, it didn't work out for us. Paper's open for questions.
Yes.
I'd like to just make a couple of points, very simple points. First of all, the carbon that we used was spectroscopic to cure Johnson-Matthey carbon, but we didn't leave it to the Johnson-Matthey people. We then analyzed the carbon, and we did it 7 times, and we got an average of 0.04 ppm of iron to carbon. Now, furthermore, the iron that we got in the detritus that dropped at the bottom was about 10 times more than the total iron of the whole rock. So this is what made us quite sure, as I think now, that iron was produced. However, I will admit the following, that we didn't do an isotopic abundance study. So it's just the Sundaresan was going home, so to speak. That's why we didn't do it. Texas A&M used to do that sort of thing very easily. But there are 4 papers now. You only mentioned Cushing and our own. There are 4 papers which have done this experiment and all come to the conclusion that there is some iron produced. I agree with you, however, that there are questions, A, the isotopic abundance, and B, the line I produced was certainly not a good line. They only had 6 points on it and they were very scattered.
I was wondering if I could ask a question. Has anybody, Monty has talking about it, but has anybody else done this Osawa experiment?
I made it so many times in so many different ways that I have no doubt about the Russian right. And don't take it as an offense, but your experiment is the worst I've ever seen. First, you didn't use carbon in the sense of one that was isotopic form, in this case graphite. Secondly, the test that you have made there says that in your carbon is such an amount of dirt that it's completely stupid to go with that stuff. You had at least to buy a very ultra-pure carbon rod, and for carbon I mean graphite. Secondly, you should certainly have listened that those reactions are called low-energy nuclear reactions. and you increase 4 times the energy. I think that this, how do you solve that you could do a better low energy nuclear reaction multiplied by 4 the energy?
What was the question?
How could you think that increasing the energy of the reaction in an experiment of low energy nuclear reaction, you could get better results than working on concrete, let's say, with 6 amps instead of 40? Is it
Well,
a contradiction?
as I said to begin with, what I had attempted to do was duplicate Osawa experiment based on the publications that I had. And the Osawa experiment that I had, the publications that I had, showed 220 volts connected across a copper plate with a carbon rod. Basically, that was what I attempted to do, was duplicate what I believed was the original experiment.
Well, I've also spoken with Mr. Cushing, and I've seen, speaking with him, that he also was not too, how to say, prepared in experimental physics. So I discarded immediately some of the suggestions he gave me, and on the contrary, worked. For example, I chose not the experiment that in the paper that probably you have seen from Mr. Cushing. You have seen there are 3 methods: air, the container of graphite, and the powder on the metal. I chose the one and the one in water and the one on the metal, and I discarded the other one because it was, in my opinion, not the best, as realized. Secondly, I take good care of starting immediately with good, not carbon, because I know that carbon, maybe there is another concept that you don't know, but there is something, which, at least in my theory, that is called the particular properties which any kind of isometric configuration of an atom has. So when you have, for example, your percent of iron in your carbon, that is not clean iron, for example. It's connected with other, is in some chemical composition. And even the carbon is not pure carbon, it's connected with some other composition. So the best way was, at least, and according to my opinion, it would have been better for you to start with 2 well-made tests, like the one of BRC and the one of...
Have you published a paper on your experiments and how you
No, I gave...
No, I gave news iron in the activated carbon.
I gave news of, yeah, I gave news of my own repetitions only in the proceedings of the first International Conference on Cold Fusion in 1991 in Como, because frankly I was not too much interested in making only iron. I get the suggestion to first to the group of BRC, and secondly to Bofis, to Sundaresan. And then I showed it to other people, because I was dealing with many more interesting things. But I followed this test, and for example, as you can see, for example, the nanometer is much better made than you say. For example, at least one thing to control. If you take a rod of graphite and make the same test that you made there, you shall find nothing on your mind. That is at least a first necessary step. That about much deal of stuff that you got means that it's not real. Okay, finish.
Yeah, you can roast me later.
This is very interesting. I think we should have a side group get together and talk about these. There's one more question back here.
Yeah, personally, I would like to see the experiment. I would like to see the experiment work. So you guys can help me figure out how to make it work.
I'd rather leave the paper from Bofis and from BRC.
Did you check to see if the iron was hematite initially? Because it sounds like you're just converting it to magnetite.
Right, that's what it looks like. No, we had an ash analysis done of the original sample, Fe2O3 was what was found in the reduction. So then we calculated the concentration of iron in the original sample based on Fe2O3.
Thank you. We have to move on to the time. Thank you again. Ken Shoulders will next discuss charge clusters and their relation to reactions.
It's a fairly optically or picture-oriented discussion. I'm Ken Shoulders. I work with my son, Steve. We have a place in Bodega, California, and we do experimental work almost entirely in a variety of things, but I would say it centers around electron clusters, charge clusters, technology. We formed a partnership with a fellow named Tom Shanks of Somerset Power Corporation, Hal Fox of FIC, and Mark Goldis and Kevin Shambrook from Magnetic Power, Incorporated in Sebastopol, California. What I'm going to try to put across here today is not easy because it embodies not one but two new fields. But I'm going to try to show you some scanning micrographs of palladium that's been treated in a variety of ways, not the least of which is a charged cluster technology that we work with. There will be a sample that's been donated by John Dash that was electrolytically treated. There will be a sample donated by Roger Stringham that's been sonically treated. And what I'll be trying to show you is that there is a commonality in all of these methods of either gaseous discharge bombardment of these samples, sonic bombardment, and or electrolytic processing. We'll do some X-ray microanalysis showing that there's new material here, or material that hides in cracks that didn't reveal itself before. That seems to be the theme of this conference. Is this really new, or was it there all along just hiding? But I'm going to try particularly to connect the notion that, I'm irradiating myself here, wrong button, to connect the notion that a fracto emission process is at the root of the electrolytic technique. But basically you embrittle the material. When it gets brittle enough, it jumps off the surface due to the extreme electron density caused by that charge separation process. One of these things that we work with called an EV, that's sort of a Latin acronym for strong electron, is created. It loads itself with nuclei found nearby. Again, I pushed the wrong button. And that then this electron cluster, which is now becomes a massive, ultra-massive negative ion, is accelerated into the surface because of this conventional nuclear reaction, having the equivalent of megavolts of energy with only local kVs applied. And that this process has a threshold energy. You can bang all day below a particular energy density, and nothing happens. If you rise above a certain critical energy density, suddenly the dirt appears. And we're going to say even that the nuclear cluster reaction itself, the fact that there's large numbers involved and some strange coherence still unknown by me, produces an effect very much like Mossbauer effect, which absorbs radiation, converts it back from a high peak energy to low peaks, so that we don't see this coming out externally. Now that's a lot to try to convince you of, I grant you. But there's another theme of this conference is you don't have to believe it. That seems to be the underlying theme. Now what we do in our world of making these charged clusters at a tremendous range of technological difficulties. On one end it's so simple, and that's all I'll introduce here today, that you can do it by shuffling across the rug here with a key in your hand and touch the doorknob. You'll make a spark. That spark contains this entity that we deal with, this EV, this charged cluster. And it's about all that's needed to do this conversion process. That will be what I'll be trying to convince you of. In this particular slide, we've taken a piece of relatively pure aluminum foil. It's shiny and bright on one side, the other side's a little bit more corrosive looking, hasn't been electro-polished. We'll put that piece of foil on the surface of any reasonable conductor, like just a plate of metal. We'll take one of these Tesla coils that you check for leaks in laboratory glass apparatus with. It's just a little handheld thing, it buzzes. And we'll make a spark, it's a half a centimeter long or so, as you hold it over. So you let it spark, 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 spark. Then you take it out from an extremely low technology and put it in a scanning electron microscope, which you've got in your closet. So this picture on the top is what you see. There's a 10 micrometer mark showing here. There's a hole in the center. There's kind of a fused ring of aluminum oxide that's been drawn back. And there are several errant marks over here that is much smaller than the main energy stripe. The extent of the hole actually goes through the foil, just due to the fact it melted in a certain way and then it refroze itself. The diameter here is far larger than the actual energy cluster that struck it. The diameter there, well, first the back side of this thing, just to show you the penetrating power. Again, the foil was 6 micrometers thick. It went through it. It had no trouble at all with that. It would go through about 20 micrometers. That's a thousandth of an inch or so of aluminum. That little tiny hole that's left in the center can be seen with an optical microscope very, very slightly. But if you put it in the electron microscope, get the tilt right, the electrons go through. So there was a hole that went completely through it. Now, of course, the aluminum is a very thermally conductive material, and it grossly distorts the actual energy distribution that's trying to be shown with these so-called witness plates. So when you put in a very high resolution test witness plate, which is made by depositing chromium on a microscope slide, and then treat it exactly the same way, just put it down on a metal plate and spark it with a Tesla coil, you'll find these marks greatly separated from each other. When you scan with an electron microscope, it's a long way between them. But you'll find very little confusion when you get to one. That's what they look like. They're a little 3 micrometer diameter cluster of pure hell. These things will knock holes through just about anything you put there, unless it's a dielectric. If it's a dielectric, the charge builds up, the EV escapes. It jumps right back off the surface. But you can see this very well-defined area. There's a few droplets always around from the molten material that's been splattered out explosively. There's a little halation often due to thermal effects and other things that have been cleared from the surface due to that local heating. But whenever I talk about EVs and NEVs, which are nuclear-loaded EVs, I'll be referring to this kind of an energy density. Everything is clustered into what amounts to about a 3 micrometer diameter active area. Now, if you change your witness plates to materials that are much higher melting point, for example, stainless steel in this case, titanium is a good example, tungsten, molybdenum, anything you wish, you'll get a crater, depending upon the conditions, that's a lot larger, flatter, most often flatter. This particular one was done on a 13 micrometer thick aluminum or stainless steel plate, and the EVs were launched or fired in vacuum. Under those conditions, you get this effect. When you look at the back side of that 13 micrometer stainless steel, it looks like you had come straight up from the bottom of the world, because it's an extremely messy situation. But it's been made messy by, there's a plateau showing here, a plate that I applied to the back side of it, because if you bombard a stainless steel foil directly, you won't be able to deposit all your energy from one of these charge clusters into it. Local charge buildup is so great, it jumps and leaves again, even on a metallic sample of that sort. So you have to back it with an aluminum plate. On that condition, all this splattered material hits the aluminum plate and then rescatters itself, redistributes. But I show this only to show you that there's a lot of penetrating power from the very simplest kind of thing you can do in air with a Tesla coil that's childish. It's practically it's a miniature Ford coil, if you've ever played with those kind of things. Now, in a very few words here, I'd like to try to summarize what charge clusters have meant to me. Now, this doesn't carry any weight in the scientific world. I just have to say that these are results that have occurred over the years. The results have remained. Very little has changed. I've been unable to move from the fact that created, as I just described them, they're about 3 micrometers in diameter, and they contain about 10 to the 12th electrons. There are not any more than 1 million nucleons of any sort, any positive charged entities at least, within one of those clusters, by the best measurements I can make. Then this allows us to have 10 to the 5th nucleons still embedded in there and not be measured so far. If that's the case, this gadget that we've just generated, this nuclear EV, acts as an ultramassive negative ion with a charge to mass ratio that's still so high that when you actually measure the velocity of this ensemble, it's equal to the velocity of an electron accelerated by whatever the potential applied is. In short, if you apply kilovolts, the ion velocity is up to megavolts equivalent velocity. It's a wonder to me this is so, but it is absolutely so. You can find these ions embedded at depths equivalent to megavolts. The reaction energies effects are megavolt in characteristic. So the thing is acting as a simple nuclear accelerator in a way that is not easily seen when you consider what most accelerators look like. And that little accelerator can carry a large number, typically 1 million or so, nucleons into the fray in one pass. Thanks to a couple of very helpful people, we had samples to work with. John Dash contributed one that was 100 micrometer thick foil. It had been made 3 years ago or so. He said he kept it in a little plastic box. He'd washed it with water. I'd asked him for one that was kind of characteristic of the business that he was in, but one that was not overly toasted, that hadn't been cooked so long that it was all battered to pieces. And I got a perfect example of what I wanted. There were a few marks here, there, and yon on this thing, not so dense that you had much overlapping effects at all. So this way I could separate whatever process I was interested in as being a very primitive, original, single-step process. Roger Stringham contributed an ultrasonically treated foil that was 100 micrometers thick. He did that one in 1996 in a particular reactor that was run with the classic methods that they've used for the years, I suppose. Now when you take John's sample and just cruise around on the surface with an electron microscope looking for evidence of fractal emission, I find it everywhere. Of course, you're free to find something else. But fractal emission is a thing that's very well documented in the literature, and I chose not to go into it in this session because many people know of it. But it's very simply a process that is mechanical in nature, in which the energy is stored by some brittle producing technique. When the brittleness arises to the point that the strain tears the thing from the surface, it does so very abruptly. A piece leaves. When this piece leaves, it produces the opportunity for charge separation. If the Lord be willing, it may be a very great charge separation, or it may be none. You may have no effect. Or at the same time, this piece that's leaving can be carrying the potential up to KV levels. It doesn't matter whether it's in a solution or in a vacuum. Same thing occurs. Then this process of EV creation occurs in this high charge density region that was produced. In this particular example, there's a mark here that I've shown down here in magnified form that is relatively characteristic of EV strike marks, but modified by the special characteristics of this surface. The special characteristics are everything is brittle and aligned in a particular way. This is an alignment direction. It's very clear. There's something about this direction. There's a metallographic streak of some sort here, a fold from the rolling. But this little fellow here and this one are what I look for when I say a surface has been struck with one of these charge clusters. However, on a surface of the sort that's produced by these craters, the chances of finding an ideal strike mark are very low because they'll be on the back side of the thing that just left. It's a very, very low probability you'll catch one of these guys unless you're looking in the solution somewhere else. That's the optimal place to find it, is the best hiding spot in the backside as it left. But what they do is spray material around. It's not easy to see here, but there's a light decoration there and around here and around this fellow. And I've used a combination of SEM and Auger It's a homemade Auger technique, but nevertheless, it's very good for seeing whether those lightly decorated areas are due to something other than the substrate material. You can't tell what it is. You can just say it is not palladium. And then we do X-ray analysis to say, oh yes, the whole background is palladium. There's nothing anywhere but in these light areas. So we have a mixture of technology here. One is we do a rapid scan of huge amounts of acreage, trying to find out what the characteristic structures are. And then we do that by Auger. Then we stop and look at the X-ray analysis of a particular one that's been selected. So this one occurs naturally in the dash type of process, and a typical analysis is shown here, which may be found in 100 places that you look around. Every time you find the evidence of this brittle fracture, you can count on seeing something. Incidentally, the choice of whether it's gallium or sodium is Mach Snakes. I don't know. It's probably sodium, but you know, the technician doing the work on this rental instrument said, well, they can't make the determination. It's probably gallium or sodium, so it was written that way. But you have this kind of distribution of material on the average. Now, if I've ever seen any process that's scattered all over the world, it's this process. Wherever I find the brittle fracture mark, I get this kind of dirt. In fact, I've come to the conclusion the earth was built by this process, because whatever comes up on these is not too far off what you find out in the backyard. So then the question falls immediately back to, well, did this stuff come out of one of those cracks? Was it hiding there all along, and I just didn't see it? And the answer is probably not, because we really look at those cracks that have not got this brittle fracture look to them. We really stop and we pause on them and analyze, and nothing's hiding in that crack. But let that crack go through one of these eruptive processes, then a new world appears. So I started in this business just with tongue-in-cheek to see, you know, where's this stuff hiding? Come on, fellas, come out. The answer was, they weren't there. They seemed to have been created. So although I represent this as an average shot, there are many other things that can happen. Now, this is not the average for what John sees. But John's sample that he showed usually is different from the sample that he sent me. The sample that he sent me was grossly undertreated from what he had said. And perhaps you get these lighter series without the heavy ones if you don't just keep going and bombarding on. I hope Professor Bacher's yawning is not an indication of my delivery, but I guess I have to accept that. He's the chairman. But you're doing good to stay awake. This is a typical X-ray analysis of a typical surface. The sample was so clean and so pretty, except for the occasional piece of dirt that was obvious, that this is all that you can see. It's palladium, palladium, palladium. Man said 5 minutes more. I do have to roar. There's a process that occurs that where you get one of these strikes, often you find, this incidentally is with an external stimulation. We purposely bombard this surface with EVs, produce these funny little marks, and the main thing that took off and left. But in this particular case, we got an exothermic-like indication. There was something very uneven-ish that occurred. Just a corridor of wildfire-like activity occurred, pulling all of the material that is still analyzed as palladium, in this case, to the side. There's a tremendous energy storage process going on at the surface. Now, it's more evident in things like this, where you purposely bombard the surface, analyze this particular area, you'll see there's something happened here, some kind of little spreading of energy. Not trying to define what it is in this talk. I'll say when you get up and closely analyze that particular sample, look at that trash pile here. You'll see there's a lot of melted laid-back material, and what you find is oxygen, magnesium, aluminum, silicon, and calcium, typically. More dirt. The dirt was not in cracks like that by the hundreds, but it did show up suddenly here. when you get that characteristic explosion. Here's an example of one of those good things that you guys would like to happen. An EV struck, there was a tremendous production of new material, yet the flake was not kicked out. It stuck on the surface. It stayed with it. All these tracks are, again, very typical of that nasty, brittle fracture type, electron producing, EV making, nuclear converting process. Well, here's an example of a wildfire, I call it runaway process. The analysis is on this track over here, produces oxygen, sodium, silicon, and gold, let's say. This little fellow here, although it's violent looking, very metallic lily was produced there. It had no interesting stuff in it. It was just thermal junk, palladium purely. But what's cute here is the way that some energy process, mechanical energy storage perhaps, produced a wildfire, I call it, of energy dump that just ran all around, ate the thing up, virtually destroyed the surface locally, as it shows here, producing this kind of a scattering of new material, but only along the lines that are basically the crack lines that were made by the hardening process, perhaps the hydrogen loading, whatever, or deuterium loading. I will have no conclusions for you to speak of. I'll say that though we see as a summary of the dash sample that there is some self-triggering process that's associated with brittle fracture. You get it up to a certain point, it'll fire. And you that wonder about this afterlife these things have, take heart. Mechanical energy is still there. If you take these things out, put them anywhere you can think of, they will fire weeks later. They're still going to be going, just due to mechanical storage. The new material has been produced that I cannot account for. New material is not produced in areas you would expect it. The most violent eruptions possible are the cleanest sometimes. And that wildfire area is not going to help you any either. And that it is possible with the techniques of external bombardment to keep the material from jumping off the surface. You can actually retain it, use it for useful purposes later, reload it. Now in the dash sample, or in the samples I got from Roger, there were several EV strike marks showing after they'd been pummeled thoroughly, beat up, and destroyed virtually on the surface. But this was the kind of evidence that you get on an ultrasonic surface. EVs have been there. EVs apparently are created by no other than that wonderful thing that happened just after the sonic collapse. When the charge density is high, as evidenced by the charge separation, you can see is light. Then the EV is created. That one is the guy that roars into the surface carrying his charge of nucleons with it. And this particular one has a pretty little decoration around it. This is an ultrasonically treated sample again of a brittle fractured light thing that came out. That little white area around it carries the same dirt signature that we see everywhere. The ultrasonic process makes the same kind of stuff that you get out of the electrolytic process, or the electrolytic process carried over to vacuum and or into air and bombarded with these EVs directly. So we have seen that there's a threshold effect that occurs around 3 cubic micrometers of material. If you go below that, we don't see it at the energy densities we've got. If you go to higher energy density, then you'll get it. As the reaction size goes up, the atomic number that we see on the products, new products generated, also increases. We're suggesting the basic process is that an EV is generated from any intense electron emission source, drugs, sonics, or what. That the NEV is made available by just simply grabbing on to whatever nuclei are nearby, running those into the surface at NEV equivalent rates, and producing the products that we see. This gives us an equivalence between the electrolytic, sonic, and any externally or gaseous generated EV type process. But the wonder here is that in the nuclear cluster reaction, this thing, this clump, that's so much to me like a Mossbauer effect, having some form of coherence, is responsible for the suppression of all these high peak energies. That's why you don't see stuff coming out of here with gammas in it, which we do not. At the critical size of the cluster for the kinds of energy densities we make must lie between about a 0.5 micrometer and 3 micrometers in size. And we're getting a surface energy contribution from where we do not know. But there's something that produces this wildfire effect that, if it could be gathered up, would be a very useful form of energy to help create an energy gain device or more transmutation. Now, go for it, George.
First,
Conclusions next year or the year after, who knows?
questions. I asked you once before, how do these electrons stick together?
Yeah.
What makes me think I'd have an answer now if I didn't then?
Well, you answered it.
Don't know yet. I've been at this a long time, but there's no clean description of why. There have been several other people's theories, and I've had 3 or 4, but I guess I change them about every year. I thought I had it all knocked down into a toric type structure. Boy, electrons were behaving well. And then the darn nuclei showed up. Now, how are you going to handle positive and negative charges in the same kind of thing?
What evidence do you have other than these appearance of elements that you showed us that do have nuclei in this?
I separate them out. I can manipulate them pretty freely. I can take them out and see who came out, or I can put them back in selectively and know that they're in there. So it's a controllable process. That's one of the nice things about working in vacuum, if you will. You see directly, by really pretty great instrumentation, the process as it occurs in real time.
If that's true, you should be able to change the nuclei and hence change the products that you see. Have you done that?
That's not the subject of this paper, let's say.
Yes.
Not the electron holding together, is it possible the electron have more speed, then current have magnetic field, then like link together on the force of magnetic field? So that's usually current always shrink together with magnetic field.
This is not a spring.
Yeah.
This cluster is very distinct.
Yeah, but you still have spike on.
There's one.
When you still have moving, yeah. When you moving have magnetic field, will hold together.
No magnetic field,
Oh,
that's
no.
obvious externally.
No, magnetic field is produced
Internal.
by moving itself.
If it's moving, it's there,
Yeah.
they say.
The whole difference.
Okay.
Dr.
Yeah.
Monti has been
In the
associated
population,
with us.
it seems that the Italian glass doesn't fit the American population. So anyway,
United States to sit, and also for the United States to trade.
They don't fit his carousel.
anyway, I said please Japanese and
Anyways, by way of introduction, Dr. Monti has been working with us for about 2.5 years. We're a crazy company, I suppose. I have been trying to get some of what Dr. Monti has been doing into established research facilities, etc. I can tell you we've been thrown out of more highly respectable institutions in Germany and Canada and other places than you can shake a stick at, but we're still stupid enough and persisting or crazy enough to get to know Dr. Monti. You know, he is controversial, he is perhaps ahead of his time or whatever, because what he has written about 8 years ago or so, or even before that, is now being repeated by people here in a different way. In other words, his initial thoughts, there has to be a possibility of low energy nuclear change are being echoed by many people using different methods, coming up with similar things. Now, without further ado, I will proceed to read the words of Dr. Monti, who may probably interrupt me anytime it suits him, but we'll see. In summary, by the way, what the purpose of this is seems to be to summarize what everybody else has been saying and is starting to say, which is the exact opposite to what he was doing when he was a renegade, talking about the very thing that we've listened to today. It's an up-to-date list of experimental tests constituting, in my opinion, a good validation for the alpha extended model of the atom. In order to explain the experimental results of L. Kebran, in 1988, I devised a new model of the atom. Now that's interesting, characterized by the following features. One, a substantial asymmetry of the Coulomb electric and magnetic fields of electrons and protons. Two, the existence of positions of stable electromagnetic equilibrium of electrons in the vicinity of nuclei. Three, the neutron is a particular bound state of a proton and an electron. Four, the nuclei are composite structures of hydrogen atoms of period 4, that is alpha extended model. 5, physical and chemical properties of each atom depend on the various possible isometric configurations. Isomeric, I'm sorry. In light of this new model, the periodic table of the elements has been reconstructed. I have seen what he's done. I don't understand it, make no bones about it, but it's interesting to hear him talk about it. This model proved itself very useful, not only in order to understand Kebran's low-energy nuclear reactions, but also to explain, in 1989, the cold fusion phenomena claimed by Fleischmann of Pons. I rummaged with Roberto through some of his possessions. I have a picture of him in a top hat and tail, chicken in one hand, egg on the other. I said, what the hell is this about? He says, well, that's an example of cold fusion. He says, every farmer can tell you, you feed the chickens magnesium, they get better shell eggs, and the eggshells happen to be calcium. At that time I wasn't swift enough to ask, did you ever do a mass balance on it? Anyways, carrying on. In 1990, I made a list of experimental tests of the alpha extended model of the atom. And that's reference 4. He's got quite a glossary behind of all the references. The periodic table of elements, now this is the new thing. The reconstruction of the periodic table of the elements, according to the alpha extended model of the atom, is very simple. And Roberto had some slides here, which unfortunately...
Yes, but I can show an example of group 1 and group O as soon as it comes to the point. Go on.
The horizontal view shows clearly that the nuclei are periodic structures of period 4. The vertical view, that is Mendeleev's order, in which only the 2 most abundant isotopes are listed, suggests immediately the composite structures of the nuclei. For example,
I share that this. For example, group 1 and group O. The only difference is the T1 part at the end, but they are completely equal. Also the building is the same, 4 alpha, 3 alpha, 3 alpha. But that only completely different chemical properties because of the T1 group, which is added to the site. That's enough. Go on.
Now we go to neutron synthesis and alpha 0 group. Neutron synthesis, which is the first step in atom building, was achieved by Borghi, starting from a cold plasma of protons and electrons. That's reference 5. The following steps: synthesis of deuterium, tritium, helium-3, helium-4 alpha, and experimental evidence of the 4 neutron, that's alpha 0 group, were already well documented in the scientific literature, as well as the production and decay of the nuclei from 11 alpha to 18 alpha, and the new radioactivities. In other words, a reversible transition. I'll let you guys figure out what that
alpha
means.
between 2 beta minus decay and the 2 electric atoms.
Everything okay?
Yes.
We then go on to experimental evidence for the low energy nuclear reactions. Nucleus plus n times 3 alpha, nucleus plus n times 4 alpha. At the end of 1989, I could get informations about the reaction. Nucleus plus n multiplied by 3 alpha, nucleus plus n times 4 alpha, which confirmed the reality of the composite structure of the nuclei. The nuclear reactions indicated were the following. 2 carbon plus oxygen yield iron, sodium plus oxygen yield potassium. The first could be very easily reproduced. Consequently, I tested it following methods 2 and 3. The report handed to me claimed the production with the same methods of 35 different elements. I noticed that all the stable isotopes of silicon and iron could be considered composite structures with carbon and oxygen.
Wait a moment. This is why I always stated that when you make a composition of the natural bundle of carbon and oxygen in natural bundle, you select the natural bundle of iron and so on. So I always was contrary to this position of the back group. We said that the composition has to be different. If you start with the natural composition of carbon and oxygen, you get the natural composition of iron. So you want.
Anyways, there's further experimental evidence for the reactions nucleus plus 3 times 3 alpha, plus n times 3 alpha, and nucleus plus n times 4 alpha. Experiments at BARC. In 1991, I gave a lecture at BARC on low-energy nuclear reactions. 1 year later, gave me a preprint showing experimental evidence for the reactions carbon plus nitrogen yields aluminum, carbon plus oxygen yields silicon, 2 carbons plus nitrogen equals chromium, 2 carbons plus oxygen yields iron, 2 carbons plus oxygen yields nickel. B, experiments at Texas A&M. It sounds like a familiar place. Immediately after this positive result, Sundarsian and Bakras repeated test 2, showing once more experimental evidence for the reaction 2 carbons plus oxygen yield iron. C, experiments by Champion and co-workers. In 1992, I informed Joe Champion about the experimental tests of Oshava, and I showed him how to use my periodic table of the elements. Champion and co-workers repeated later, that is in 1994, method 3, with the following results. 1, using the carbon arc, new elements produced were a whole bunch, zirconium, molybdenum, rubidium. The carbon nickel carbon arc produced another bunch of different ones, as you can see if you look at the screen. The carbon copper carbon arc.
You go lower a scroll back.
All right. How's that? Better? This makes it easier.
Can you speak up just a little bit? Or?
All right, though. This fell over. Anyways, then comes, there's no point 4 on the report, I guess it got scrubbed. We're dealing with point 5, cold fission. The low energy nuclear reactions listed by Kebran were all reversible in accordance with the alpha extended model. In other words, according to Roberto's chart, you can make it, you can go back to the original. I summarized all the biological low-energy nuclear reactions indicated, together with a particular low-energy reaction, the half fission. And there we take a complicated lead and make 2, whatever they are.
You break lead 206 and you come out with 2 10345 rockets.
Obtained by electromagnetic excitation of the lead nuclei. Moreover, old and new radioactivities showed a very good experimental evidence for spontaneous cold fission, followed by the transition.
Out.
6. Low-energy nuclear fission of stable isotopes. A. Experiments at Texas A&M and Engelhard laboratories. In 1992, I was invited by Dr. Bakras to witness experimental tests suggested by Joe Champion. The first of these tests told immediately to me what was going on. I had already seen it in a drawing made 500 years before. And here comes Roberto the alchemist. We forgot to bring his hat and coat.
Not only, but this is like an open book. For example, this is an indication about the time of the reaction, because it's wood. Only wood can stand the reaction has only two minutes. Also, those symbols have an exact meaning. Maybe cow can understand them. If not, I like better for the moment not to tell. But everything will grow as a particular meaning, if you can read it.
All right, back to the text. The same experiment repeated at Engelhard laboratories showed conclusively the reactions of splitting mercury to platinum or gold minus an alpha particle, and taking 109 silver minus alpha to 105 rhodium.
Palladium. 1,546 palladium. No.
That is, the possibility to cause alpha decays of stable isotopes by means of ordinary chemical reactions, and that's reference 9. Now we go to point B, which is more elaboration on experiments by Champion and co-workers. In 1995, Mr. Champion noticed that one of his mercury cells, designed to make platinum by electromagnetic excitation, was producing rubidium. Well, okay, I don't know my elements, I just write checks. At a rate 10 times bigger than that of the TT, platinum, giving further confirmation of the reality of the half-fission nuclear reactions indicated by Kervad. It is easy, in fact, to notice that the half-fission of this, that, and the other element results in something else, which you can see on the graph.
Well, all these elements are exact half of the mercury. The routine is just half of mercury for each isotope. Only two isotopes remain out, which are 199 and 201, because if they go more easily and after decay, they get into platinum and gold. So,
the problem is it's so frighteningly logical that it can't be real. The two remaining isotopes of mercury 199 and 201, by the induction of an alpha decay, produce platinum and gold. 7, carrying on. Low energy nuclear reactions of unstable isotopes. The possibility to cause nuclear fission of stable isotopes by ordinary chemical reaction suggests immediately the possibility to cause the fission of unstable isotopes. A series of experimental tests made in 93, 94, 95, and 96 gave me very useful information. In addition to what I have shown last year, I can say that the amount of thorium oxide in the thorium ash was 78%. Consequently,
one moment. I would like to remember that last year I was not able to say how much thorium was in the thorium ash. Finally, in an Italian laboratory, I could have a good analysis, and now I know that the percentage of the thorium ash was 70% of thorium ash. No, 78% of thorium ash. I remember that we supposed when we repeated the experiment in Texas and that could contain a maximum of 2 grams. That's the reason why when Lin found the 2 grams in the slag, said that probably all the thorium was there. No, the thorium was 7.8 grams, of which 5 grams disappeared.
Anyways, I know about those experiments. I've done about 10 myself. It's amazing. The radiation goes by. We're now financing tests at 2 different laboratories, one in the United States, one in Italy, where we're trying to do a complete and decisive mass balance. And if we're successful, maybe we have something to talk about. At this stage, we're experimenting and collaborating. Anyways, today, that covers the sentence which Roberto calls today, September 96. I'm waiting for definitive results from 2 national laboratories. I guess we're about 3 months away from a make or break situation to show whether Dr. Monti's efforts...
Yes, I would like to say about this. With our analysis, we found such astonishing results that they seemed incredible even to me. So I prepared all 5 complete sets of elements. I asked the laboratory to analyze all the components and then give me the before and after and the total balance, including the smoke, which has to be collected and analyzed. So,
anyways, reactions of mercury-sodium in 1995, Joe Champion showed in Colorado Springs the possibility to obtain the following reactions. 198 mercury plus sodium yields 197 gold, and magnesium or yields platinum and aluminum, simply making an amalgam of mercury and sodium. I repeated the same test after a few months in a condition of sodium excess. Well, you should have been there. We have a little lab where Roberto worked, and it almost blew up, and the smoke was ferocious, but the results were interesting. The result was the production of the following elements: silicon, potassium, calcium, iron, titanium, chromium, and copper, and who knows what else.
Yes, as usual, the check looks only for gold, and look also for other elements found immediately of this because they were very good.
Yeah, Dr. Monte's periodic table suggests immediately further tests of this kind. For example, mercury lithium, mercury potassium, mercury Rb, mercury carbon. Thank you. Which can be easily performed. Now, next goes to point 9. Cold fusion is another example in metal lattices. When Fleischmann and Pons published their experimental results about the cold fusion, D plus D in palladium lattices, I had already published in Italian my new model of the atom and the periodic table. Consequently, it was easy for me to understand what had really occurred and where Fleischmann and Pons were wrong. I explained these facts for the first time in the Erike conference in Italy in spring 1989, which didn't make Dr. Monte popular with Fleischmann and Pons. In 1991, I gave the following written explanation at the second ICCF at Como in Italy, which is referenced as item 4. A, palladium does not only act as a catalyst of the deuterium plus deuterium reactions. B, as a consequence of the nuclear reactions among PV and LiOD, the palladium was burning like a match, forming at least within a thin layer a plethora of new nuclei. And this apparently is what other people are now talking about. In order to limit the nuclear reactions, I suggested to use monoisotopic electrodes and to analyze the atomic and isotopic composition of the electrodes before and after the reactions. In 1996, Mizuno et al. Made this test with the following results. Within a thin layer of 1 micron, they found about 15 different elements. A similar test was made by Bakras and Minevsky with the following results. Within a layer of 1 micron, they found a whole lot of different elements. The starting concentration of palladium was 99.8%. The various different reactions can be singled out using the periodic table and finding the exact isotopic composition of each new element. I think what you're saying, Dr. Monte, if people had access to your charts of your atomic table, they could pretty well predict what they're going to get out of.
You can say only, for example, iron. You have to know which item goes to the table, then you can go to the element it comes from.
In other words, one of these days, when your chart gets accepted, you will be able to help everybody predict and make what they want. Number 10, isomeric configurations of the atoms. The alpha-extended model allows each atom to keep in storage within its, quote, rigid, tridimensional structure, the, quote, information which determines its physical and chemical behavior. In 1991, I suggested that the two allotropic forms of the carbon atom, diamond and graphite, were a good example of this kind, and that this example should be only the first in a long series. This opinion has recently been confirmed by the experimental results of S.K. Dixit in the Rasasastra Department of Alchemy of the Banaras Hindu University, where it is normal practice to obtain different isometric...
Isomeric. Oh, it's a...
It says metric, sir.
No, this is a mistake.
Okay.
That's the mistake.
Configurations of atoms and molecules characterized by different physical and chemical properties. From the most common configurations, the same atom or molecule is given a specific name according to their various isomeric configurations, which prove useful in the medical field. I suppose that's no different from the Eskimos having 27 different names for snow. A few months later, in October 91, I could get information about the discovery of a third isomeric configuration of the carbon atom. Fluoriness obtained by the arcing carbon in helium atmosphere. Finally, in 1995, I was informed by D. Hudson about the discovery of new peculiar isomeric configurations with monatomic transition elements, which he called ORMES, orbiturally rearranged monatomic elements. These isomeric configurations are well known in alchemic literature
But according to the alpha extended model of the atom, the right name for these isomeric configurations should be ERMES, electronically rearranged monatomic elements. Okay. Conclusion. The experimental evidence listed above constitutes, in my opinion, a good validation for the alpha extended model of the atom. Signed in Bologna, not Bologna, in July 19th, 1996. I hope I did well enough.
Any questions?
Yes.
How can we get this chart, Dr. Monty?
What?
How can we get a copy of this chart?
Well, I had to send it to you. Unfortunately, I had some pieces of the chart, but that instrument doesn't work. Anyway, well, if you want, I can send you a photocopy. By the way, I would be happy to set now, in this moment, to see on KillNet. If we can agree on this, I give you the copy. Okay. Anybody else?
What role does the electrolyte play, or does it make any difference if you have heavy water, light
if you
water?
notice, the electrolytes are all from the same group: lithium, sodium, potassium, and you can try also with rubidium and cesium.
Right. Well, what about the deuterium versus light water?
But deuterium has a particular active. It is one of the. To explain this, I should show some parts of the table. But deuterium is the terminal part of many of the less abundant isotopes. So it's some kind of a particular brick which constitutes the structure of a nucleus.
In your experiments, transportation experiments, what's the largest amount of original starting material that you have managed to convert?
Well, my largest amount, usually I make experiments because they are of about 1 kilogram, and sometimes or about 5 kilograms.
Now, how much do you get
For what?
of transmuted material?
As I said before, I sometimes some results that I don't dare to say until they are better confirmed.
No, I just want to know.
Well, I can say
is it 100 ppm, 1000 ppm, what sort of thing?
For example, with gold, I'm usually around 600 parts per million.
600?
600. I can go better. The test of which I want to be controlled 5 times from Italy is, for example, when I had to change, because when I saw that most of the remaining thorium was on the slag, I devised a new composition of the mixture, so that now, for example, I have a slag of 100 grams and a metal of 300, 400 grams. And to change this, without my intention, I found a strange result, which, as I said, it was so surprising that even if I knew something about it from the chemical test, that I don't dare to say, but anyway, I tested it 3 times at the moment, and all the 3 times came the same result. But still seems to me so unbelievable that I want to have it repeated at least 5 more times.
Incidentally, if Dr. Monty appears to be hedging, that's because I'm asking for hedge.
Well, no, anyway, the result was simple. I started with 100 grams of silver, and I ended with 200 grams of silver.
Have you convinced Dr. Perperata of your theory?
I was asked with Perperata some years ago in Perugia. Dr. Perperata now, years ago, we were quarreling with each other. Now he's always, when I'm speaking, he's very quiet and silent. I'm usually for him, but
I don't believe it.
I don't believe that.
I don't believe cold dealing.
No, I tell you, he made a lot of noise in Perugia, but while I was speaking, he went out. No, the reason is very simple. In 1989, I went to Milan to suggest him to make the experiment carbon plus oxygen, and he said that he was crazy. Now he has seen the results of oxygen and the others, so now he's very silent.
Thank you again.